Yeah, can others please mute themselves? So today's topic on what I'm going to do is called as neural architecture search, or NAS also. In short, not to be confused with network attached storage, which is also a term quite closely related to the at least the hardware side of when we create these deep learning models. Now, the purpose over here is that so one of the questions which you guys have been asking me while I've been going across the different networks was like, what was the rationale behind design? So how many layers do I take? How many neurons or how many number of convolution neurons or convolution kernels do I take per layer? This was a pertinent question which you guys have been asking, and most of my answer, or practically the only single way answer I've been giving you till now, is that it's a designer's prerogative. The designers had experimented around some different combinations of these things, and then they found out that this is the one which was working out good. They've got the best performance, so they put it out over there. In fact, like that's one of the reasons in early days people would just call deep learning as some sort of black magic or sorcery, and sort of a field which was heavily dominated by people who had a lot of compute power. And that's how these data companies like Google or Facebook or Twitter, they actually made a long lead way into it because they did have a lot of servers with them and a lot of compute power available. So essentially they were all rich in these kind of servers, and because of that they could really get it working. Now the point is, currently we live in a world where we are not so rich in servers. I mean, most of us, some of us are, and we can experiment out in the same way along a whole plethora of architectures. And even if we, I mean, currently my lab runs at about 1 petaflop of compute, and even if we run at 1 petaflop of compute, I mean, sooner or later we also sometimes run out of options, and because there are a lot of people who keep on using that 1 petaflop as well. So sooner or later people do run out of options because there are a lot of users also logged into it. Now for that, what we came out as an idea was that can we have neural architecture search to do it, and what I'm going to discuss is based on a very popular paper called as EfficientNet, which has a very generic way of search by scaling. Now, while I get you introduced onto that, now for neural architecture search, there are basically a couple of objectives we need to keep in mind. So one is that how will you scale or how will you search for these architectures? One is you can base the search, so you where your search is essentially based on cost of compute. It can be based on say model size or space complexity, which is the total operational space complexity of inference, It's cost of compute at inference. So we are not typically much worried about the training part of it because that's a once in a while affair. So once you train a network, then that part of the compute as well as space, those requirements are completely gone, and then you don't need to worry about it. But definitely, like when you're doing an inference, then you will be calling that over and over again, and that's where you really need to be worried about it. Okay. Now, broadly, these are two objectives based on which we look into these models and how we do it. Now, let me give an example. So let us take an example of scaling depth. And then let us see this one. Okay. So say that and I will take a very simplified example so that it's not very complicated for everybody to understand and we can achieve our objectives very easily. Okay. So say that I have a network over here, which is X, and then I essentially run it through a set of convolution kernels. So this is P1, P2, PK. Wait. Plus is after it, so it will be convolve with this one plus this results in this one. Okay, and what we are doing is essentially this is with a stride equal to 1 and pad is equal to floor of W by 2. So if I do this kind of a stuff, then essentially I will get down the same kind of an output. It's just for the sake of simplicity. Now, in this model, so this is going to be my model 1. Okay. Now, if I find out what is my cost of compute or total number of max, so I can write down my number of fuse, multiply, and add operations, or basically number of unitary operations if I just write it down. So how many operations are involved over here? How many additions? How many multiplications in this whole process? Tell me how many number of multiplications are involved in this process? Hmm? Please repeat it once again. I could not hear you properly. Please repeat it. I could not hear you properly. Others, what happened? Have you forgotten this by now? All the complexity analysis which we had done.
So 2kCWH into m minus h plus 2pH divided by stride plus 1 and n minus w plus 2pw divided by stride plus 2.
Oh, you told me a lot of things. So the number of multiplications. So let me write it this. So the number of multiplications is going to be C W H. This whole thing and k number of times because that is what it is going to do, and multiplied by size of output. So this is mn. Okay, and number of additions, just in case of convolution, it is going to be kcwh cwh minus 1, and this whole times mn. Okay, and plus there will be another k number of additions. So my total number of operations becomes something like kcwh mn 2kcwh mn minus mn plus k. Okay, so if we put some values over here as an example, an example is where your C is equal to 3, K is equal to say 64, M is equal to N is equal to 2 to 4, and W is equal to H is equal to 3. Then what would this value come up as? I think here I wrote it wrong. It will be for each of them CWHMI and then there is a K. Minus KMN which is equal to KCWHMN minus KMN plus K. So please tell me, what is this value going to be?
Sir, it's like 170 million. 170,197,056.
Approximately 170 million. Okay. Now, let me go from here onto another model. So in the next model, what I do is Okay. So here, let us count this number of ops. So say number of multiplications, number of additions. So what will be my total number of multiplications? So let me indicate this is what corresponds to over here. This is what corresponds to here. And what will be my total number of additions? So this corresponds to this layer, and this will correspond to this layer over here. So this will be this whole thing which comes down. So my total number of ops So what is going to be my total number of ops in this case, where my values are almost the same as what I was using. The number of Ks is still 64, the C is still 3, and M cross N is 224 cross 224, and I have all of these balanced stride of 1 and a balanced padding given down. So now can you tell me what will be my total number of ops which comes over here?
Sir, one question.
Yes.
That K times 1 minus Mn, 1 minus Mn would be negative.
Yeah. That will be subtracted over there.
Achha.
Hello, sir.
Yes.
Sir, like, are these calculations exact? Like, instead of Mn, shouldn't it be like, sir, like M minus H plus 2 pH upon SH plus?
Why will it be so?
So, like, the resultant, the size of the resultant, tensor would be like the height and width would be like M minus H plus 2 pH upon SH plus 1, right? So that many number of.
Just look over here. I said that it is operating with a stride of 1 and there is a padding of floor of W by 2. Now, if you do that,
Okay,
what will
got
be the
it.
size?
Yes, got it. Yeah.
So one more question on the previous previous ones. We'll just go. Thank you. That addition of that plus K term, that will be a broadcast term, right? Shouldn't it be K with all the elements of Mn?
How many additions are you doing for the biases? There are K number of such bias elements available.
But we have to do with every 2D element of the.
Right? How many neurons are there? See,
Oh, achha,
you have
sorry.
a constant bias for every. So you're essentially getting down a scalar value as a result of this convolution, and then you are adding this term onto that, and that is contributing to one single location. The second one is going to the next location, next channel at the same location.
Yes, yes, got it. Thank you.
I'm going to iterate over all of these things throughout the class so that to a certain extent you get over a lot of misconception you have. The problem with teaching deep learning to a class is that everybody comes with a lot of misconceptions given the amount of ill-posed information available flooding the internet. And every other guy claiming to be the deep learning guru, I don't know what they did ever. I'm not the guru, I'm still learning because this thing which I'm teaching you right now is something which finally I figured out how to crack it about some 5-6 months ago. So we were working on this thing for a network design, a very important part of an IP design in compression engines. We finally managed to crack it 6 months ago in terms of like when we knew in and out what is going to happen and we had a full control of what we want to do on top of it. And it took us practically 3 months to write the paper which describes all of this. I'm trying to run it as a tutorial. This will take me 3-4 hours to finish off. So
can you please move to the next slide?
yeah.
So is it 2 billion, sir?
Sir, I got 3.86.
Sir, excuse me, sir. Sir, I have a doubt.
Yes.
Sir, in addition part, sir, we are writing it as k CWH minus 1 mn plus k into 1 minus mn. So, sir, are we doing something wrong? Like, sir, in the last slide, we have k CWH mn plus k into 1 minus mn. So, sir, that's simplified.
Oh, wait. Yes, that -1 should not be there. That is my mistake. This one, right? This should be gone.
Yes, sir.
Yeah, put down all of those values. So your C is equal to 3, M is equal to N is equal to 224, K is equal to 64, W is equal to H is equal to 3. That's what we had, if I remember. Yeah.
Sir, I got 3.87 billion.
You got
3.87 billion.
1 billion. Which seems to be very unlikely. Can somebody check?
So these k number of additions are just for one cell of m cross n of that cube which we are getting as output. So while we are not multiplying with mn k mn like this, in the last slide when we calculated the number of addition, so it was k into we did k into CWH minus 1 into mn for addition.
Right. Plus KMN. So if we do that, then I think this picture erases out. So it essentially becomes KCWHMN, right?
Yes.
Yes, I think this was what I was. Yeah, thank you.
So even I can be wrong. So there is nothing about that. No, because I'm not even I'm instantly deriving them. I am not even coming up with a notes or something because this architecture search is something which is live on my mind. So this is going to be KCWHMN plus KKWHMN. Okay. Now tell me, what is that number of hops?
So can you go to
It's
the next
about
page?
2 billion.
Hmm?
It is about 2 billion, sir.
2 billion.
Yes, sir.
2 into 10 to the power of 9.
Yes.
Okay. Now say that I extend it further. Okay. To something which I call as another model, which is model 3. So in model 3, what happens is I have this X. From here it goes to this sol conf and then plus bias. This is my P. It produces Z1, which again goes through my conf layer, which is P, and the bias produces Z2. Then again, sorry, I should mark this as convolution operation. Then this whole thing again gets convolved with another layer plus a bias and produces my Y. Okay, so if I go with my number of hops over here, so in this layer of operation, so my number of ops is equal to going to be 2kcmn 2kcwhmn, right? Am I right over here for this operation?
Yes.
Okay, here it is going to be 2k square WHMN. Here it is going to be 2k square WHMN. Okay, so now if I write down my total ops of this network, this is 2kcwhmn plus 4k square WHMN. Now put down the same constants over here and now tell me what is your number of operations coming down over here. The same operating characteristics as in the previous one.
Sir, around 7.5 billion.
7.5 into 10 to the power of 9. Okay. So now from here, let us look into comparing these. So number of ops on model 2, it was 2 billion. $170 million. Now, typically, like if you look over here, this is much lower since low number of input channels. That is precisely the reason why this was much lower. There was no other reason for this one. Now, if I go by this, then let us look into what is the depth of this model. So here my depth of model is 3. Here my depth of model is 2. Okay. So now if I do like this, that what is my ratio of depth of, let me go to the next page itself. So if I do it like this, which is number of ops in model 3 divided by number of ops in model 2, which is equal to 7.5 by 2 into 10 to the power of 9. How much is it?
15.
15.
No, sorry,
So
3.75.
3.75.
Now if I do like this, which is depth of model 3 of model 2. So that is 3 divided by 2. What is this?
1.5.
1 point? 1.5. Okay. So I'm not exactly seeing much of a like if you clearly look over here, one of the things which you can do is like you can say that if I sort of like scale my model by certain factor, then I'm going almost a double of the scaling of that factor coming out over here. Okay. Now, if I keep on increasing these models, so what I do is now I go and take an approach which is sort of a modular design, because till now we are not actually in very deep networks in any way. So now say that I create this as a modular block. So what I'm doing is I have my X. So I keep on exposing these to multiple modules. So there is conf1 module, output goes to conf2 module, output goes to conf3 module. Like this, it keeps on going up to CD1 module over here. And then I get my output, which is Y. Okay. So typically, if I follow down the same convention, my number of ops is going to be what? This will be 2KCWHMN plus you will get down D1 minus 1 times of, so twice D1 minus 1 times of K square WHMN. Do you think I'm right?
Yes.
Okay. So if this is the scenario, now say for my depth, say I put down the same kind of constants over here. So if my depth, which is D1, in one of the cases is 100 and one of the cases is, or say D2 is, just make it in terms of D so that I don't confuse the number of elements. So in another case, this is 150. Okay. So now let's look into what will be this ratio of network 1 to network 2. So this is ops with net D1. So what will be my total number of ops over here? So this KCWH anyways is a very negligible quantity. So this is approximately equal to 2 into 99 times K square WH MN. And if I do an ops of net underscore D2, then that is approximately equal to twice 149 times K square WH MN. Now if I take a ratio between ops of net D1 is to ops of net D2, then what is this going to be? So your K square CWH, these things, K square WH MN, and these two, they are all going to cancel off each other. This becomes equal to
0.664.
This is the same as 99 is to 149, which is approximately equal to 100 is to 150. So you would get down that this is approximately equal to D1 is to D2. Do we get it? Look over here. Will it be so?
Yes.
So from here, we can come up to an observation and a statement whereby, and then this will obey only for a very deep network. So in case of in case of like deep networks, say depth greater than 30 or so, we will have number of ops is proportional to depth. So what I'm essentially saying is, if net underscore D1 is scaled to a new depth D2 is equal to some alpha times of D1 to obtain net underscore D2, then the number of operations in net underscore D1 is to number of ops in net underscore D2 is equal to, sorry, this is scaled, so I will put down D2 is to D1 is equal to alpha. Can I write this statement? Can I write this statement?
Yes, sir.
Okay. Now from here, let us again take that modular derivation. So considering the same modular derivation. So what I had was essentially number of ops is ops of a network with certain D is proportional to it was 2 times D minus 1 K square M N. This is what it was. Okay. No, K square CW K square WHMN. WHMN. Okay. So now if I change, so now say for K1 is equal to 64 and K2 is equal to no, sorry, not K2 is equal to 128. Okay, so if I do this one, then what will happen? So I will get down I'll get down a network which is net underscore D underscore K1. This is net underscore D underscore K2. I get down two networks. Okay. So if for each of them I look into number of ops, then what is this going to be equal to? So I will have twice that D minus 1. This K is going to become 64 square WHMN. And here my number of ops is going to be 2 into D minus 1, 128 square WHMN. Okay, so now if this is the scenario and I do this ratio, you would see that number of ops for net underscore D underscore K1 is to number of ops for net underscore D underscore K2. This is equal to this, everything cancels out, so this is equal to 64 square is to 128 square, which is essentially equal to K1 square is to K2 square. Now if this is the scenario, then what I can write down is if net underscore D underscore K1 is scaled along its width by a factor beta to obtain net underscore D underscore K2 such that K2 is equal to beta times K1, then this number of ops for net underscore D underscore K2 is to number of ops for net underscore D underscore K1 is essentially equal to beta square. Can I write it this way?
Yes.
Okay.
Yes.
So this is an important piece of derivation. So essentially what you see is that for very deep networks, if I have a certain ratio in which I want to increase the depth of the network, then my total cost of compute is proportional to the depth of network in some way. And if I'm increasing the width of the network, which is I'm increasing the number of channels by a certain proportion, then my total cost of compute increases by square of that proportion. Okay. So this is where I will close for the day. We will start from this point where we will come to an important derivation in terms of that if I do both with depth and with scaling, then how will it increase? Okay. So we'll close for the day and tomorrow I will start again from this one, which is going to be the essential derivation of something which we call as efficient net scaling rules.
Sir,
Yeah.
so when we scale the depth, right? So it is going to be proportional to the depth ratio, right, sir?
Yes.
But in our example, it was like double of it, 1.5 and 3.75.
No. So that's what I was saying. So in case of shallow networks, it will not be so. That's the reason why we went on to deep networks, where what happens is that this is what we call as an ingest layer. This initial conditioning over there, as well as the final conditioning, which goes on to show the final output. Now for the ingest layer and the output, excluding that, all of these processing layers, it will just depend on that. So the scaling is done essentially in the processing layer over here. I'll come to that. This the design part is not yet over. There is a trick. There is a way in which you will have to design the network. You cannot just have anything being scaled anywhere.
Okay, sir, got it, sir.
So one thing like where you showed us the model like C1, C2, there we came up with the operation number of operation equals to total 2 times KWH like multiplied by C plus D1 minus 1. So I've combined the all terms. So if we take the ratio for two models now with different D1s, then this factor C number of channels in the initial the input will also be a deciding factor. So if it is more than 64, then taking above 30 will not guarantee that a doubling of, like, it won't be.
So typically, I mean, the reason why we were limiting it to that is that these are things which were done on natural images, which have C, which is either 1 or 3. And when you say that C is, I mean, my initial input tensor's number of channels is of the order of 64 or something. That is very rare. I mean, even if I do a multi-sequence MRI, then whatever we know, the maximum we can reach up to is 7 channels.
Okay.
Yeah, but then you can come back and say that I can have a hyperspectral image over here, and a hyperspectral image can have like 1,000 different channels because each will be corresponding to a different slice of the wavelength being imaged. In that case, it's not going to hold. So you'll have to get back to the drawing board and do it. All of this is for natural images where the input number of channels is about 1 or 3, much lesser.
Okay.
So 30 is what we start with. I think when you have it in 30,